to Math 7. I'm Mrs. Campbell, and today we're going to be talking about outcomes in a sample space. Specifically, we're going to be looking at tree diagrams. Let's get started. Let's start by looking at a definition of compound events. Again, so compound events are when two or more events are happening at once. Rolling two dice, dealing a hand of cards, even picking out your toppings on a pizza or a sub, maybe. So what are tree diagrams? Let's define those as well. So tree diagrams are a way to show the outcomes of simple and compound probability events. In a tree diagram, each outcome is represented as a branch on a tree. And they're super easy and they're super fun. Let's look at an example. If you toss a coin 2 times, what is the probability of getting 2 heads? This question asks us to use a tree diagram to find our answer. Now, this is an example of independent events because the outcome of one event does not affect the outcome of the second event. So when you flip the coin once, you have an equal chance of getting a head or a tail, which we'll call H and T. Now on the second flip, you also have an equal chance of getting a head or a tail. So in other words, whether the first flip was heads or tails, the second flip could just as likely be heads as it could be tails. Now you can represent the outcomes of these events on a tree diagram. That's what the question asks us to do. So let's take a look at it. Here's our question again. If you toss a coin 2 times, what's the probability of getting 2 heads? So here's the tree diagram for this example. And I'm just going to start by reading the blue notes that you see here on the side. It says the probability of getting a head on the first toss is 1 out of 2, or 1/2. See it going up to the H there. Okay, so starting with heads, the probability of getting a second head again would be 1 out of 4. Because we have 1 over 2 times 1 over 2. So there's another half there. Now, how do we calculate the probability of getting 2 heads? So these are independent events. And since the outcome of tossing the first coin doesn't affect the outcome of tossing the second coin, this next slide will show how we can calculate this probability. Let's look at that tree diagram again. The question again reads, how do we calculate the probability of getting 2 heads? So again, these are independent events, and since the outcome of tossing the first coin does not affect the outcome of tossing the second coin. So again, here's the equation is the probability of A and B. Well, the probability of A, we said, is 1 out of 2, and to get heads again, the chances are 1 out of 2. So when we multiply them together, we get the probability of A and B is 1 over 4. So we can calculate that the probability of getting 2 heads when tossing a coin twice is 1 over 4, or 25. So there's a 25% chance. Let's look at another example. Jessica has 4 different favorite types of ice cream. She loves vanilla crunch, black raspberry, chocolate chip, and lemonade. She also loves 2 different types of cones, a plain cone and a sugar cone. Given these flavors and cone choices, how many different single scoop ice cream cones can Jessica create? So to solve this problem, we're going to do a tree diagram. And first what we need to do is list the choices of ice cream. We have vanilla crunch, black raspberry, chocolate chip, and lemonade. Next, what we're going to do is add the 2 cone types. Now, each flavor has 2 possible cone types. Remember, sugar and plain. So, from each flavor of ice cream, we're going to draw 2 branches, 1 for each type of cone. So, vanilla crunch, sugar, plain, black raspberry, sugar, plain, and so on and so forth. So, there are 4 different flavors and 2 different types of cones, the sugar and the plain. So, which means that we have 8 possible ice cream cone options. Vanilla Crunch Sugar, Vanilla Crunch Plain, Black Raspberry Sugar, Black Raspberry Plain. You can see there are 8 possible outcomes. So notice that the number of choices multiplied by the number of variables equals the total number of possible outcomes. In other words, the flavors times the cone types equals the total of possible outcomes, or 4 times 2 equals 8. Pretty simple. So in our example, we had 4 times 2 equals 8. So this, what we see here, the 4 times 2 equals 8, this is called the fundamental counting principle. And it can be really, really useful if you don't want to draw an elaborate diagram to figure out all your options. And it's also a great way to check to see if your tree diagram has all the possible outcomes. Good way to check your work. Let's look at another example. Suppose you flip a coin and roll a die at the same time. Show the sample space of possible outcomes. What is the probability that you will flip a head and roll a 4? Again, these are independent events, and they occur when the outcome of one event does not affect the outcome of the second event. So rolling a 4 has no effect on tossing a head. And our job is to draw a tree diagram to show the total number of possible outcomes in the sample space. There are 6 possible outcomes on a die, 1 through 6. And 2 possible outcomes on a coin, heads and tails. So here's our question again, just if you need to refer to it. The question is, what's the probability that we will flip a head and roll a 4? So here's the tree diagram for our example. Here are the possible outcomes for the die, 1 through 6. And here are the possible outcomes for a coin. So there's a probability that we would have roll a 1 and toss a heads. There's a possibility that we could roll a 1 and toss a tails, and so on and so forth for each number on the die. All right. So basically what we're doing is we're multiplying the probability of the first event by the probability of the second event using the counting principle that we used in the last example about ice cream. So the probability of getting a head, or A, is 1 out of 2, and the probability of rolling a 4, B, in our equation, that will be B, is 1 out of 6. So the probability of event A and B using the distributive property would be the same as multiplying the probability of A times the probability of B. So the probability of tossing a head is 1 to 2. The probability of rolling a 4 is 1 out of 6. So the probability of tossing a head and rolling a 4, it's really simple. All we have to do is multiply those 2 probabilities. So 1 over 2 times 1 over 6 equals 1 out of 12. Now, this works because if we look at the tree diagram, there's only one time where we get a combination of a 4 and a head. And there are 12 possible outcomes, 1 out of 12. And this little note on the right is asking you to look up here. There's 12 possible options, and the possibility of the die being a 4 and a head is only one of those 12 options. So we've checked our work, and our work checks out. All right, everyone, that just about does it for this lesson. Thanks for joining us, and we'll see you next time. Bye-bye.